All right, guys, before we get started on this, there are a few parts of these problems that we have to skip. We haven't done them yet. So I'm looking at part B for question 2. We haven't talked about Taylor polynomials. That's like chapter 10 stuff for us. And same thing for part C. Nothing about Taylor polynomials for us in this chapter. I think that was it. Okay, 1, 2, 3. I thought. Oh, there we go. Okay, so I just wanted to go through this. If you needed some help looking at these, our test has questions not exactly like these, but very similar. You're going to be doing this type of stuff for the Chapter 6 test. So we're given this differential equation. On the axes provided, sketch a slope field for the given differential equation at the 12 points indicated. You have to sketch a slope at all the points, and then sketch a solution curve that passes through the point 0, 1. So first, calculate all the little dy dx's. I'm going to start when x is 0. When x is 0, the slope is always negative y, and you can do work off to the side. You don't have to show work. But at 0, 0, the slope is 0. At 0, 1, that's 0 minus 1, so the slope is negative 1. 0 minus 2, negative 2. I'm going to go over to the negatives here. Negative 2 minus 0 is negative 2. Negative 2 plus 1 is negative 1. And negative 2, oh no, sorry. Did my math wrong on that. I should probably be writing this out. Negative 2 minus 1 is negative 3. Negative 2 minus 2 is negative 4. They'll just be looking for slopes to be getting steeper. And then when x is 1, so we get 2 minus 0 is 2. 2 minus 1 is 1. 2 minus 2 is 0. 4 minus 0 is 4. 4 minus 1 is 3. 4 minus 2 is 2. It's got something kind of like this. So that's the slope field. And then remember to plot the point 0, 1. And just let the tangent slopes kind of guide you. You can even let your curve go through these other points. For a slope field, we don't know what is happening beyond this little range of 12 points. So do not put arrows on either end. You just connect the slope field like that. All right, part B. The solution curve that passes through the point 0, 1 has a local minimum at x equals ln of 3 over 2. What is the y coordinate of this local minimum? So if we had a y equals equation, we could just plug in x and see what y comes out to. And your first thought might be to find what y is. But if you take a look at dy dx, it's pretty tough to separate this. We don't have anything to factor out. We can't add y. We can only multiply or divide. So we actually don't have the skills to separate and integrate this. So instead, we have to think about, well, what else are we given? So we have a local or relative minimum at x equals ln 3 over 2. So what do we know about dy dx at a relative minimum? We know that dy dx should equal 0 or undefined. In this case, we don't have any undefined slopes, but we do have places where dy dx can equal 0. So we can set dy dx equal to 0. So 2x minus y has to equal 0. And then in this case, solve for y. So y equals 2x. So the question was, what's the y coordinate of the local minimum? And now we have an expression. Y is equal to 2 times whatever x is. So y is equal to 2 times the natural log of 3 over 2 at the local minimum. All right, part C. Oh, this was B. So part C says let y equal f of x be the particular solution to the given differential equation with this initial condition. Use Euler's method, starting at 0, with 2 steps of equal size to approximate f of negative 0.4. Show work. I always start by showing what delta x is equal to. It's always your desired value minus your starting value divided by the number of steps. So in this case, delta x is negative 0.2. All right, and then the buildup of this. So remember, you're starting at 0 and you're going to go one step negative 0.2. So the first approximation is f of negative 0.2. You start at f of 0. You add to that delta x times f prime of 0. I would suggest always writing out this little formula before you plug numbers into it so that you're not plugging the wrong numbers into things. All right, they gave us f of 0, it's 1, plus delta x is really minus 0.2. And then f prime of 0, so we need to find f prime of 0. So off to the side here, f prime of 0, remember that's the point 0, 1. So our equation is 2 times x minus y. So f prime of 0 is equal to negative 1. So the first approximation, the first step, is f of negative 0.2 is about equal to 1.2. Right? And then we jump off from there to find the next step. So go another negative 0.2. You'll be at f of negative 0.4, which is what we want to find. That should be approximately equal to f of negative 0.2 plus delta x times f prime of negative 0.2. Again, you're going to have to do this work off to the side. So f prime of negative 0.2 is equal to 2 times x minus y. So negative 0.4 minus 1.2. So f prime of negative 0.2 is negative 1.6. Delta x is negative 0.2. F of negative 0.2 we found was 1.2. If it's easier, change these to fractions. 0.2 is 2/10, which is 1/5. This isn't too bad though, but depending on your decimal without a calculator type thing, 16 times 2 is 32. Remember this rule, how many decimals do you have? That's how many decimal places you should go. So this is 1.2 plus 0.32. Or again, just use fractions to begin with, that's fine. So f of negative 0.4 is about equal to 1.52. Right, what else do we have to do? Find the second derivative in terms of x and y. Determine whether the approximation found in part C is less than or greater than f of negative 0.4. This is an old question that's based on concavity. If the graph is concave up at the approximation is lower than the graph, it's an underestimate. If the graph is concave down, the approximation is an overestimate. We can actually answer this without the second derivative. Take a look at our sketch. The entire curve that goes through the point 0, 1 is concave up. So our approximation, without even finding the second derivative, our approximation is an underestimate. But I'll go in order. So find the second derivative. So let's see. Let me write down the first derivative first. So dy dx is 2x minus y. And the second derivative, so take the derivative with respect to x of both sides. That would make 2x 2, and minus y is minus 1 dy dx. And we need this to be in terms of x and y. So remember, you always sub in the expression for dy dx. So 2 minus 2x plus y if you distribute the negative through. So there's the second derivative. Now, we don't want to plug in our approximation value to see what the sign comes out as, but normally we would test the point of tangency, which we can still do. If we plug in 0, 1, the second derivative is positive. So you could say this, second derivative evaluated at 0, 1, because that's our point of tangency that we know is on f of x. That's equal to 3, which is greater than 0. But this is honestly optional because I would just say the slope field shows f of x is concave up at x equals negative 0.4. It's really at more than that, but this entire curve including this specific point we're talking about, like right here-ish, is concave up. So the slope field shows that f of x is concave up at that value. So therefore, the approximation is, and I always have to sketch this, an underestimate because the line is lower than the graph. So I underlined the keywords there. Slope field's concave up, shows that it's concave up, therefore we have an underestimate. Okay, that's it for that question. On to the next question. So again, we're skipping part B. We don't know how to do that yet. So consider this differential equation. Y equals f of x is the particular solution. Here's an initial condition. Use Euler's method with two steps of equal size, starting at -1, to approximate f of 0. Start with finding delta x. Begin with your desired approximation. We want to find f of 0. We're starting at -1, so subtract -1 and divide that by the number of steps. So delta x is positive, which makes sense because you're going from -1 up to 0. All right, and then we start with we're starting at -1, so add 1/2 to that. Your first approximation is f of -1/2. Starts at f of 0, starts at f of -1. Add to that delta x times f prime of -1. F of -1 was given as 2. Delta x is 1/2. F prime of -1, we've got to do the math off to the side here. So the order pair is -1, 2. So 6 times -1 squared minus -1 squared times 2. So 6 minus 2 is 4. So f of -1/2 is approximately equal to 2 plus 2, which is 4. And then we add 1/2 to that, so then we're at f of 0. That should be about f of -1/2 plus delta x times f prime of -1/2. So we've got to calculate that. 6 times -1/2 squared minus -1/2 squared times y, which was 4. Did I get that right? Yeah, times y. So 6/4 is 3/2 minus 1. 3/2 minus 2/2 is 1/2. Okay, so f of 0 is 4 plus 1/2 times 1/2. 4 1/4, I would just call it 4.25. Or 17/4 if you want. All right, we're skipping B and then doing C. Find the particular solution given the differential equation with this initial condition. So find the particular solution is separate, integrate, celebrate. So remember to separate this, your only options are multiply or divide. And you first have to factor this anytime you have x's and y's together. So dy dx factored is take out an x squared. You get 6 minus y. And then you can separate by dividing by 6 minus y. Then you're going to integrate. We've done this a lot of times now. The integral of 6 minus y is negative natural log 6 minus y because u is 6 minus y, du, dy is -1, and you've got to balance out the negatives. You don't have to show all of that, but you do have to have the negative there in your answer. Integral of x squared is x cubed over 3 plus c. Get rid of the negative first. My pen doesn't really want to work properly for some reason. The negative only applies to the x term, not the plus c. Base e both sides. 6 minus y equals c times e to the negative x cubed over 3. Plug in the initial condition to find c. So -1, 2. So y is 2. And x is -1. So when we cube -1, we're going to get -1, and there's already a negative built in, so it's 1/3. So 4 divided by e to the 1/3 is c. And then that brings us to our y equals. So now I would add y to this side. It's going to be 6 minus, and then I'm going to subtract c over here. So 6 minus 4 over, maybe I'll write cube root of e. That's c, times e, this is ugly, to the negative x cubed over 3 equals y. You don't have to bother simplifying that at all. I would just leave it as is. Okay, and that was it for this question. Next question. Consider the logistic differential equation. That means that we have information from here. Now, be careful with this. It's not quite in the proper form. Let me go back to our logistic notes. Maybe. So here are some logistic notes. The form, this needs to be a 1. So we have a little bit of work to do in order to reveal what actually this is. So let me go back to this. Okay, so before I can get this into a nice format, I really need to say, let's factor a 6 out. This is really 1 minus y over 6 if you factor a 6 out, right? So if you factor a 6 out, 6y over 8 times 1 minus y over 6. Of course, 6 over 8 will reduce. We're going to need to be looking at that to probably answer some of these questions. Okay. All right, so I just wanted to take care of that before I dove in too far. A slope field for this differential equation is given below. Sketch the possible solution curves through the points 3, 2, and 0, 8. Notice above 6, there's this horizontal asymptote. So the point 3, 2 is kind of barely marked off here. Just follow these little slopes here, but don't go beyond that horizontal line. And remember, no arrows. 0, 8 is also marked off. So that horizontal line, again, is your, like, kind of think of it as a fence. It's not going to cross down through. That's all we had to do with part A. Okay, part B is use Euler's method again, starting at 0, 2 steps of equal sides to approximate f of 1. So begin with delta x. You want to approximate f of 1. You're starting at 0, and you're doing 2 equal steps. So delta x is 1/2. Starting at 0, the first approximation would be f of 1/2 is about equal to f of 0 plus delta x times f prime of 1/2. F of 0 is given as 8 in this problem. Oh, no, wait. Yeah. F of 0 is 8, so be careful of that. In part A, they gave us this other point, but 0, 8 is at the top of the page. Okay, so f of 0 is 8 plus 1/2, and f prime of 1/2. So we've got to plug in, oh, I'm sorry, it's not f prime of 1/2. It's f prime of 0. So we've got to plug in 0, 8 in here. So we've got 8 for y, so f prime of 0. Say you plug it into the original. 8 over 8 times 6 minus 8. That's 1 times -2. So f of 1/2 is about equal to 8 minus 1, which is 7. Then we find f of 1. We take another step. So that's about equal to f of 1/2 plus delta x times f prime of 1/2, which again we've got to figure out off to the side. So f prime of 1/2 is y, which is 7, over 8, times 6 minus y, which is 7. That's -7/8. So 7 plus 1/2 times -7/8, which is -7/16. Not very pretty. 7 minus 7/16. Now, you don't have to simplify your answers, so don't bother wasting time doing 7 times 16 and adding all of that up. That's good enough. Okay, and then we're not doing part C. Part D, what is the range for f for t greater than or equal to 0. So again, use the slope field, but also pay attention to which curve you're on. 0, 8 is officially the point that's on the particular solution. So you're on the top curve. So what is the range for t greater than or equal to 0? Now, greater than or equal to 0 does not include this top part. So the highest point is 8, and then it's going to approach 6 without hitting 6 necessarily. So the range, I would say, is, I would just use interval notation, but you could use inequality notation, but I would just say the range is from 6 to 8. Or you could say 6 is less than y, which is less than or equal to 8. Either way. All right, last problem. I think last problem. Here's dy dx. Y is the particular solution. Here's an initial condition. For this particular solution, f of x is less than 1 for all values of x, so that's interesting. We'll figure that out in a minute. Use Euler's method starting at 1 with 2 steps of equal size to approximate f of 0. Show work. Begin with delta x. You're trying to approximate f of 0, and you're starting at 1. So 0 minus 1 over 2 equal steps is negative 1/2. That means that starting at 1, if we go back 1/2, our first approximation is f of 1/2. That's going to be f of 1 plus delta x times f prime of 1, which we'll need to figure out off to the side. Y is 0 when x is 1, so dy dx is 1 minus 0, which is 1. F of 1 is 0 plus, no, not plus, minus 1/2 times 1, so f of 1/2 is negative 1/2. Right? And then the next would be, again, we're subtracting a half from there, so we're trying to find f of 0. We should jump off from f of 1/2 plus delta x times f prime of 1/2. Find f prime of 1/2 off to the side. Dy dx is 1 minus y minus negative 1/2. 1 plus 1/2 is 3 over 2. So negative 1/2 plus negative 1/2 times 3 over 2. So this is negative 1/2, or negative 2/4 minus 3/4 is negative 5/4. F of 0 is approximately negative 5/4. Part B says find the limit as x approaches 1 of this expression. Oh, now we haven't done L'Hopital's method yet, so we actually need to put a pin in number in part B as well. If you plug in 1, you get 0 over 0, which is indeterminate. We could probably reason our way through this one, but this is meant to be L'Hopital's, so I'm gonna wait on this one. All right, so skip B. This is a chapter 8 thing for us. Okay, part C, find the particular solution given to the differential equation this with the initial condition this. So last thing to do is separate. So dy is going to get divided by 1 minus y. That's going to equal 1 times dx. Integrate negative natural log of 1 minus y equals x plus c. Get rid of the negative. It only applies to the x. Base e both sides. 1 minus y equals c e to the negative x. You can solve for y if you want to. Plug in the initial condition, which is 1, 0. So y is 0 when x is 1. We've got to solve for c. Now remember, c e to the negative 1 is like c over e. So multiply e to the other side, and that makes it y equals 1 minus e times e to the negative x. That looks pretty gross. If you want to work on it, you can say e to the, add these exponents, 1 minus x. I would prefer that, but you could leave it unsimplified in its weird form as well. All right, that finishes this packet. So I have several parts that I skipped. There's nothing like that on our test. It's just that we used to do this in chapter 10 instead of in chapter 6. So that's it.